Hi there. Welcome to the stream. Um, so today we'll continue explore mathematical analysis by Zorich, Volume 1. This is a fantastic set of texts on analysis. In my opinion, perhaps the perfect balance between calculus and mathematical analysis or real analysis. So without further ado, let's get into today's main topic, which is the property of limit. This is chapter 3, by the way, chapter 3 in Zorich. I know this is perhaps not the latest version. I was informed that in the comment section last time that apparently there's new editions in Russian, but I will just use the English edition, okay? So here we have, last time we defined limit. Let me just briefly write the definition again, okay? Because last time we spent a lot more time on the motivation. And where's blue color? Okay, I'll have to get the blue color again. Yeah, last time we spent a lot of effort in motivating the definition. Indeed, it is not the most obvious definition, and it is a definition that involves a mixture of quantifiers. So the limit of xn equals a. This statement is the same as for every epsilon greater than 0, there exists a big N, and sometimes you can write big N as a function of epsilon, because typically big N depend on epsilon. In the set of natural numbers, such that for all n greater than big N epsilon, we have xm minus a absolute value less than epsilon. Or you can describe it verbally. It says every neighborhood of big A contains all but finitely many terms in the sequence xn. Contains all but finitely many terms in the sequence xn. So let's draw a picture for that. So that's the real line. And this is the point A. Okay, and this is an arbitrary neighborhood. A plus epsilon, A minus epsilon. Okay, and a neighborhood is always an open set. And you got these points inside. Put a bigger dot here. That's it. That's the biggest. Okay, fine. The points are in there. So basically, these are the sequence members x of n greater or equal to big N. Is it greater than big N? They're all in here. Outside, there might be finitely many. So all but finitely many sequence term. Finitely many, and we don't care about them. So the definition of sequence only care about what eventually happens. That's the key here. Okay, so remember from proof writing, the basics of proof writing, we said that whenever you see a for all quantifier, okay, this is a reminder from proof writing tips. Oh, did you hear the cat? Proof writing tip says for all epsilon greater than 0 would lead to a statement like let epsilon greater than 0. This means let epsilon be an arbitrary but now fixed positive real number. And we wish to demonstrate that for this epsilon, for this now, you can treat this as a constant now, the property that follows the quantifier holds. Okay, and the existence part, existence big epsilon greater than 0, to show this part you need to write something like define or pick big N to be what? You have to either give a clear number or demonstrate or a set of numbers, okay? Or let's say big N satisfies a certain condition and why this big N actually exists. Okay. And then so it then follows another universal quantifier then follows. So you're going to do the same thing again. You're just going to write let or suppose big N greater, little n greater than big N epsilon. And that's basically it, right? That's basically you want to demonstrate the inequality holds true. So that's the process, okay? Even though this looks a bit scary, but you get this, get used to this very quickly. And in fact, this is perhaps the most important skill in analysis, is to handle mixed quantified statement, a statement with a mixture of quantifiers. There's tons of statement that looks like this. And in fact, I hope we will get there, because today, well, I hope I'll get to the definition of Cauchy sequence, which also look like this. Oh, no worries. Yeah, I believe it was you who requested the stream on Zorich, right? This is for you. So, yeah, so a bunch of examples. Example 1. Example 1, the limit of 1 over n is 0. And here's a quick proof. Let epsilon greater than 0, following our template. What should we pick? What big N should we pick? Let's do the scratch work on the side, shall we? Scratch work. Okay. Here, scratch work. What do you need? Well, we need 1 over m minus 0, absolute value to be less than epsilon. This is what you need. So how can you get there? Well, you just pick, this is just 1 over n on the left hand side. So n is just greater than 1 over epsilon, and you're done. So we can just pick big N to be greater than 1 over epsilon. This big N obviously exists. Well, not obviously, but I mean in this level, we still wish to justify why such big N exists, right? So we can define big N, or shall we say pick, you know what, choose to say pick. And it's just a stylistic choice. Okay, let's pick big N in the set of natural numbers to be, pick a value such that big N greater than 1 over epsilon. Yeah, 1 over epsilon, exactly. And we can comment that this exists due to Archimedean property. And Archimedean property guarantees that for any real number, for any positive real number, there is always a natural number that is greater. Okay, so this is Archimedean property. It is a consequence of the. It is a consequence. I mean, of the. Hang on a second. The least upper bound principle. Yeah, you can prove the Archimedean property from the completeness axiom. Archimedean. because we skipped first chapter actually, which is a little bit of a shame. I think you can mostly just study the rest of the chapter, and whenever you need a property from the real number, you go back and see if that's actually needed. I think the first chapter is actually quite important. It's a shame that we skipped it. Okay, perhaps we will do a more in-depth look later. The property of real numbers, or the treatment of real numbers, is by no means trivial. Okay, it's actually a great problem for centuries, defining real numbers. But here we're just quoting the properties. Now, Archimedean property. Okay. And now let little n greater than big N, then 1 over n minus 0, absolute value is 1 over n, which is less than 1 over big N, less than epsilon. Yes, Zorich has proved the Archimedean properties. Yeah, so therefore, by definition, here, by definition, the limit of 1 over n is 0. Very simple example. Next up, example 2. The limit of n plus 1 over n is 1. Okay, so once again, start with the scratch work. The scratch work is n plus 1 over n minus 1. This is what we want. Minus 1 to be less than epsilon. We want the error to be small. This way, the left-hand side is 1 over n less than epsilon again. Now, so this is just the same as earlier. So you can pick n to be 1 over epsilon once again. So really, there's no difference there. So you can just pretty much recycle what we have earlier in the previous proof. And now write the rest. Let little n to be greater than big N. Then the absolute value of n plus 1 over n minus 1, absolute value, is 1 over n, which is less than 1 over big N, which is less than epsilon. So we're done. By definition, the limit of n plus 1 over n is 1. And that's it. Okay? This is example 2. Example 3. Example 3, the limit of 1 plus minus 1 to the n over n quantity is 1. So once again, it should be clear that you can use the same starting sentence, but let's just do the scratch work, okay? Because after taking absolute value, this is 1 over n again. So this is, you want this to be less than epsilon, which is the same as 1 over n less than epsilon. And of course, n greater than 1 over epsilon seals the deal. All right? So basically, you can recycle what we have earlier. Same choice of big N. Okay, so then you have no, it's not given by Archimedes, right? Archimedes didn't know the property of real number, but the same idea was given in his work on arithmetic, I believe. Yeah, you can look up the history of the so-called arithmetization of the real line. Arithmetization of the real line. This is something of great importance in the late 19th century in the study of Fourier series. So there are various individuals, including Cantor, Dedekind, Weierstrass, involved in the project. I don't know who named the property. Okay, but then again, okay, let's continue. 1 plus minus 1 to the n over n minus 1. That's just 1 over n again, which is less than 1 over big N, which is less than epsilon. So therefore, by definition, the limit of 1 plus minus 1 to the n over big N is 1. That's it. Okay, this is example 3. Example 4, the limit of the sine of n over n is 0. Okay, so here, let's do our scratch work again. We want sine of n over n minus 0 absolute value to be less than epsilon. Okay, here we see a little bit of a different situation compared to our previous problem. In our previous problem, what we really did is to simply simplify the inequality. Okay. So in fact, for all the earlier examples, the inequality goes both ways. Right? Often this is not quite possible. And here we see an example for that. We just need a sufficient condition. That's why I only draw an arrow from one direction. Okay. So how can we get a sufficient condition? Because we know sine of n is bounded by 1. Is bounded by plus or minus 1. So you just need 1 over n to be less than epsilon, and that's enough. Okay, so recognizing common bond is bond in this. Okay, this is bond, common bond. Sine of n absolute value less than or equal to 1 is crucial. Okay, so there you go. Let's write it up. Actually, same first sentence. Interesting. Right. Then what? Starting from here, then sine of n over n minus 0 absolute value. This is less than or equal to 1 over n. And that's pretty much it. Okay, this is less than 1 over big N, which is less than 1 over epsilon. Therefore, I always feared analysis because I thought what was being proved was too obvious to start with. No, don't. I'm not sure what you mean, but let's say if you already know this, then this is kind of obvious. But you know, you can say that about a lot of math subject. Once you get it, it just feels obvious. But let's try to put ourselves in a beginner's shoes. Yeah, so this is done. Okay, next up. The next question is perhaps interesting. Example 5. This is the limit of 1 over q to the n equals 0 if q absolute value is greater than 1. How do we prove that? Well, how do we prove that? Well, here Zorich quoted a property from the real number chapter. Okay, so let me just quote it from, because we didn't go through the real number chapter, but basically, let me just go back to, it's in subsection 2.24. Okay, I'll try to find it. guys. I think, yeah, this is perhaps a non-trivial example. 2.24. Where is that? Subsection 2.24. I strongly recommend you open the textbook yourself, because I can't show it for obvious reason. But I strongly recommend you go through the textbook yourself alongside with me. Okay, it's not that hard nowadays to find it, but I will just not show it. Okay, I'm still trying to search for the property. Where is that? 2.24. Has to do with power of real numbers. It says there's a lemma here. In 2.24, there's a lemma. Let me use a different color. We need a lemma from subsection 2.24, which says the following. It says if a real number q is greater than 1, then for every positive number, then for every x greater than 0, there exists a unique, okay, this notation stands for there exists a unique integer k in Z, in unique integer k such that q to the k minus 1 is less than or equal to x, and is less than q to the k. That's a lemma here. Okay, so why don't we just prove it here? Okay, so that's interesting, right? This is a lemma. This is a lemma. Perhaps we should first use the lemma to prove the example number 5, and then we'll prove the lemma, shall we? Yeah, now we know where the lemma is. Let's first use the lemma to see why this is helpful. And can we do the problem without the lemma? Right. So these are nice questions to think about. Chad, do you still find this problem obvious now? By high school, this equals 0. You can say that. But that's not analysis. That's hand waving. Right? So this is actually not obvious at all. So let's start with that. Okay, so do the scratch work on the side. What do we want? We want 1 over q to the n to be less than epsilon. To get that, we need what? We need absolute value, actually. Yeah, so this is the same as 1 over epsilon less than q absolute value to the n. The thing is, how do you know this n exists, right? You need this lemma. So now you can use the lemma. We don't really care about this side of the lemma. Oh, actually we do. Actually we do. Here x, we don't really care about this side of the lemma. We care about this side. This inequality. Right? So we need, basically you pick x to be 1 over epsilon. And now this big N exists. Now this little n exists. So we're done. Okay, so yeah, let's write it up. Let epsilon greater than 0. You pick big N such that big N such that big N satisfies the inequality such that 1 over epsilon is less than Q absolute value to the big N, right, by lemma exist. Okay, big N exists by lemma 2 point by lemma from section 2.2.4. Okay, nice. And now let little n to be greater than big N. Then we pretty much have what we want. So you have 1 over q to the n minus 0 absolute value is 1 over q absolute value to the little n. Okay, and since big N, little n is greater than big N, and q is absolute value is greater than 1, so therefore this is less than 1 over q absolute value to the big N, which is less than epsilon. So we're done. Right, so the lemma pretty much is the key here. Can we do the problem without the lemma though? We'll come back to the proof of the lemma in a bit, but can we do it without the lemma? Let's do a proof 2 without the lemma. Okay, so what I was thinking is, this is not the proof in Zorich, but I think we can use another property. So there's something called the Bernoulli's inequality. So this is something called the Bernoulli's inequality, and it reads like this. So 1 plus x to the n is greater than 1 plus nx. Actually, you know what? I think I should probably prove it. Okay, I'll write it here. This is our lemma. Bernoulli inequality. Well, actually, just write Bernoulli inequality. Here, what the chat says, let K be the smallest element of S. Yeah, so it's great. It's basically you use the least upper bound property to prove the lemma. So, I mean, right now I'm still not getting into the proof of the lemma yet. I'm just using it, and I just want to use a different method. Okay, the Bernoulli inequality says, oh, by the way, some people might wonder, why can't we just use log? Why can't we just say, oh, big N is greater than the log of 1 over epsilon with base q absolute value? Because log is undefined yet. There's no such thing as log at this stage of the problem. We really starting the theory from scratch. Okay, in high school, you know how to manipulate the log function, assuming it already exists. Here, there's no such thing as log, sine, none of those things. Okay, yeah. So basically, we only use the tools available. The inequality says 1 plus x to the n greater than 1 plus nx, where n is 1, 2, 3, and so on. Okay, and you can quickly prove it using the induction argument. Induction on n. So when n is equals 1, that's the base case. It's trivial. Oh, actually, should be greater or equal to. n equals 1 is trivial. All right, so inductive case, assume this is true for n equals k. Inductive step. So assume this is true for n equals k. So assume 1 plus x to the k is greater or equal to 1 plus kx. Yes, exactly. Analysis is really going back to the Stone Age. How do you reconstruct everything? Yeah, I believe there was this German mathematician called Edmund Landau, not the Russian physicist Landau, okay, but the German analyst and number theorist Landau. He was a friend of Einstein. Landau wrote a book called The Foundation of Analysis on the number systems alone. So he went back to the very beginning, constructing the natural numbers and the rational numbers and the real numbers and complex numbers. It was a whole book. It's a classic, just on number theory. In the preface, he was like, my daughter in the university, she majors in chemistry. She thought she understood the differential and integral calculus, but she didn't even understand why x times y is y times x. Okay. I don't agree with the tone, but it's the very foundation of analysis is not trivial. That's the main point here. Yeah. All right. Assume this is true for some little k in 1, 2, and 3. Okay, and want to prove this is true for for k plus 1. Then what? Then 1 plus k. Actually, you know what? I should probably assume x is greater than minus 1. In preface, he said every high school should include chorus. I don't share that sentiment, actually. I don't share that sentiment. It's like saying every elementary school book should start from the piano axiom and construct the natural numbers. As ridiculous as that sounds. But, I mean, it's a nice book, but, I mean, I don't appreciate the tone. Okay? Perhaps that's just me. It's totally fine. Let me just say this, okay? You can tell the time without knowing how to build a clock. Right? If someone whose main priority is applied science, and he or she has no responsibility to, or to say, I mean, perhaps no responsibility is a bit too strong, but he or she can do still perfectly good work in his own field without knowing, say, the foundations of the real numbers. Right? At some point, for example, if you're a chemist and you want to solve, say, Schrodinger's equation and all sorts of approximation in quantum mechanics, you need functional analysis, and then it's perhaps a good time to study a little bit of a real analysis as well, to see where the fundamental ideas of not quantum mechanics, but functional analysis came from. So that's what I'm saying. I mean, we are applied mathematicians. I'm not saying you are. I mean, I am. I learned pure mathematics on a need-to-know basis, and I don't feel any shame about that. Okay. Anyway, so this is 1 plus kx times 1 plus x. Okay, so this is 1 plus kx plus x plus kx squared. You see, there's also danger in overemphasizing formalism. Formalism is a check on intuition. That's it. It shouldn't be fetishized. The reason why real numbers and the foundational analysis become such an important problem is because calculus is so useful. Calculus is so damn useful that we worried, what if something goes wrong? And that's why the rigorization began. You don't start with rigorization. You don't start with, that's the thing. Like in practice, if you start from regularization, you always demand that, you paralyze yourself. Okay. Anyway, so in the inductive step is now proved. So basically, this is the end of the proof. But let's try to be as thorough as possible and give a conclusion and say, don't just stop here. Okay, give a conclusion by the principle of induction. By the principle of induction, applied mathematician needs to be equally skilled when it comes to constructing proofs as pure mathematician. Full stop. Okay, but we don't need to fetishize rigor, and at least not one side of rigor. Rigor is of course important in applied work. In fact, applied science should be more, if not less, rigorous than pure math because it has real stake. Right. So we have the formal rigor. Okay, the accuracy of your definition, making sure that your deduction is airtight, that sort of stuff. That's formal rigor. But there's also modeling rigor. Right? Does your model correspond to reality? And also the rigor of, should I dare say, social responsibility. Because models are neutral. Models, which part of reality you decide to model is not neutral. Collecting data, making interpretations, these aren't neutral fact. These aren't neutral act. What kind of ramification does your model do to the world? Right? These are the kind of things applied scientists has to wrestle with every day, and they demand no less rigor than this little deduction. Right? By the principle of induction, 1 plus x to the n is greater or equal to 1 plus nx. Okay? For all n equals 1, 2, 3, and so on. So the bottom line is, whatever game pure mathematician plays, applied mathematician should be equally competent, and other things. So, yeah. Anyway, coming back to proof 2. So, use the Bernoulli inequality. What can we say? Well, we're dealing with power here. Yeah, in your childhood always thought x times y equals x. There's nothing wrong with that. If the length and breadth values of rectangle are interchanged in the same area. Exactly. That's the intuition. But the thing is, corresponding a length to a real number is difficult, right? Chat. You're totally right. That's exactly the intuition. If you calculate, yeah, it's like you have a rectangle. The area don't change if you push it like this. If you lay it down like this. First they stand up straight and then you lay it down. Of course they have the same area. The problem is associating lengths with real numbers because of this thing like square root of 2. Right? This is a real line. This is 0. This is 1. You can perfectly construct square root of 1. This is square root of 2. You can perfectly construct it geometrically. But you know, if you only accept rational number, there's no such length, right? So that's the issue. So we wish to, the whole project of arithmetization of analysis, this is what I call historical term, arithmetization of analysis, is to do away with geometric intuition. It's not that geometric intuitions are evil or not important. It's just that the idea is you construct the real numbers axiomatically and then use this axiomatic system to model geometry. Okay, anyway, so let me just I'll not erase this. Okay, I want to emphasize why we're being perhaps a little bit pedantic, because we don't want any kind of circular reasoning. No, everything should be The thing is, in analysis, pictures are kind of like illustrations of a novel. The plot should be independent of them, but extra illustration should help us engage with can help us engage with the main story. Okay, so use the Bernoulli inequality. Can we get a new bound or something like that, right? So what we want here, we want the same thing, which is 1 over q to the n absolute value less than epsilon. Okay, and to do so, we just need q absolute value to the n is greater than 1 over epsilon. But to get that, we can use a Bernoulli inequality, right? Because we can write this as 1 plus q absolute value minus 1 to the n. Okay, so if, say, 1 plus n times q absolute value minus 1, if this is greater than 1 over epsilon, then we're done. And you see, I'm applying the Bernoulli inequality. This is x. Q absolute value minus 1, this is x. And then you can solve for little n from this inequality here. That's 1, actually n is greater than 1 over epsilon minus 1 over q absolute value minus 1. There you go. So let's start. Okay, so that's our choice based on the Bernoulli inequality. Okay, so here we go. This is the proof. Let epsilon greater than 0. We're going to pick big N in the set of natural numbers such that big N is greater than 1 over epsilon minus 1 over q absolute value minus 1. Big N exists due to Archimedean property. All right, and let little n be greater than big N. Then what? Then our main objective is still 1 over q to the n minus 0. Okay? So this is just 1 over q absolute value to the n. And this is what? This is 1 plus q absolute value minus 1 to the n. And by the Bernoulli inequality, this is less than or equal to 1 over 1 plus n times q absolute value minus 1. And since n is greater than big N, this is less than 1 over 1 plus big N q absolute value minus 1. And use the assumption on big N. I might need more space. Alright, so yeah, this is less than 1 over 1 plus 1 over epsilon minus 1 over q absolute value minus 1 times q absolute value minus 1. So this simplifies to epsilon and we're done. Therefore, by definition, the limit of 1 over q to the n is 0 and we're done. So that's the second proof, using the Bernoulli inequality. All right, so let's come back to the proof for the lemma. Okay, let's come back to the proof of the lemma. So how do Zorich settle this? So here we need a property from the real numbers, that is to say, the least upper bound principle. Okay, how do we do that? Well, first of all, what is the least upper bound principle? The least upper bound principle says if a subset of real is non-empty and is bounded above, then it must have a least upper bound. So we're going to use that property here and prove the lemma. Okay. So here, we're dealing with powers. So why don't we investigate the set of powers? So claim the set of this form q to the k, where k is integers, is not bounded above. This is a subset in R. Okay, is not bounded above. And this is really easy. We use a contradiction argument. So I assume for a contradiction, or to make the flow of the proof a little bit nicer, let's write to see this. To see this, assume for a contradiction that this is not true. Assume for a contradiction that the set has an upper bound. Right. Then it has a least upper bound. Right. It is not bound. It is bounded above. So, for a contradiction, assume q to the k as an integer. Yeah, basically. This is not trivial because rational numbers don't behave this way. In rational numbers, you have holes essentially, right? It has a least upper bound in the set of real. That's the key here. Rational numbers don't have that property. A bounded set in a set of rational numbers don't necessarily have a least upper bound in the set of rational numbers. So that's the important distinction. So q to the k, where k is in Z, is bounded above. Right, then by the least upper bound principle, or the completeness axiom, it really depends on how you formulate the theory. Okay, it is possible to prove the least upper bound principle, say from other form of axiomatization. Okay, least upper bound principle is one possible starting point, but it's not the only way to present the theory. Okay, so I'm not going to bother checking whether Zorich used this as a theorem or an axiom. Let's just use the least upper bound principle, because for sure that's more fundamental than this lemma. Okay, it has a least upper bound, say S, basically the soup. Okay, so it has a least upper bound S. So what would that mean then? Because it's a least upper bound. So here, by the way, Q is positive. Q is positive. So since this is the least upper bound, then Q over S is not an upper bound. Since Q is greater than 1, so S over Q, this is less than S. So it is not an upper bound. Since it is not an upper bound, therefore, thus there exists m. There exists m in the set of integers such that s over q is less than q to the m. Right? But immediately this gives us a problem because s is now less than q to the m plus 1. Q to the m plus 1 is a member of the set. This violates the assumption. Because this is in the set q to the k is in big Z, which is a contradiction. Why do we need a contradiction here? To show the claim. I'm following Zorich, okay? I'm following Zorich. This is the original proof in Zorich. We first claim this is not bounded above. Okay. So S could not be an upper bound of the set. So therefore, this is a contradiction, and therefore the set, and thus it's the same argument you prove the Archimedean principle is also a contradiction. Assume the set of natural numbers is bounded in R, and then you have a contradiction. It's the same idea. Is unbounded above. All right, so that's the first paragraph in the proof. Okay, so here, our goal is to show there exists a unique k such that this is true. Okay, so, and then it says in the textbook, it says since 1 is less than q, it follows that when m is less than n, can you continue the stochastic calculus videos, please? Yeah, I know, right? Yeah, I should. Actually, next week we will do a series of live streams on the stochastic calculus used in physics, such as the Langevin equation as well as Fokker-Planck equation. Because right now I don't have dedicated time for preparing a video. So I figured, of course, later I will consolidate the live streams into more compact form, in a video form. But as I was doing those preparations, I might as well show the process. So we're in a stage we're almost ready to see some applications of stochastic calculus, and in physics and in finance. So we'll start with some physics. So yeah, chat says, can we say something like this? S is the set M in Z such that Q to the M is greater than X. By the Archimedean property, S is non-empty. Hang on a second. How do you know that? Archimedean principle says the following, okay? It says for every x in real, there exists an integer or natural number such that m is greater than x. How can you use the Archimedean principle here? That's my question. You're saying is for every x, there exists m such that q to the m is greater than x. But that's what you're trying to, part of the thing that you're trying to prove. The lemma says there exists unique k such that this inequality holds. This is part of the inequality. You're assuming that. Of course, lemma says more. Uniqueness also, and also the inequality on the left hand side, but you can't just go from here. That's my take. So chat says by the Archimedean property, S is non-empty, meaning there exists a little m such that q to the m greater than x. But that's what we're trying to prove. Okay, we haven't finished this proof yet. Okay, here we only showed that the set of numbers in the form of q to the k is non-empty, is not bounded above, right? When q is greater than 1, it's not bounded above, and we managed to show that here. I still haven't done the full proof yet. Okay. Yeah. So you see, because we're using things that are so obvious, quote unquote, it's easy to make the mistake of circular reasoning, because this is something we want to prove. Okay, so this is the first paragraph. Okay, just the claim that we managed to show q to the k is not bounded above. Yeah, because log is not being defined, right? Exactly. There's no such thing as log yet. Okay, we live in the middle of in the medieval time, but somehow have the access to set theory, no access to log. Imagine putting yourself into that situation. Okay, so here the next paragraph says the following. Okay, I'll just writing it down and see chat, and I'll do it myself as well to see if there's anything wrong with it. Oh, you didn't get why q to the m is greater than s over q. That's a great question. Q over s, s over q is not an upper bound for this set. Right? It is not an upper bound for this set. That means there is a number in this set that is greater than s over q. Okay, so here, let me pair that with a picture here. Pair that with a picture, so this is what it's about. Okay, so q to the k are a bunch of points on the real axes. Okay, suppose it has a upper bound, say s, right? Suppose it had an upper bound, say s, then s over q is of course less than s. Okay, so let me add a little inequality here. Since q is greater than 1, then s over q is less than s. Thus, s over q is not an upper bound, because s is the least upper bound. That makes sense? Oh, hi Tab, thank you very much for joining the stream. Yeah, because it's the least upper bound, and now q over s is less than s, therefore it is not a upper bound. So you can get, so this s is here, okay? S over q is here. So that means you can find an element in the set that is greater than s over q. So you get this inequality, and therefore from that you can deduce s is less than q to the m plus 1, but that's a contradiction. Okay, so far we only show that the set q to the k is an integer, is not bounded above. And now let's proceed. So next up, Zorich says, since 1 is less than q, then q to the m less than q to the n if m is less than n, m and n are integers. Yeah, I think we can use that. Yes, Chad, you're totally correct. So that's exactly the argument. Okay, so next up we have this sentence. So this is correct, right? This is just the monotonicity. Okay. And it says, hence we have also shown that for every real number c, there exists a natural number. There exists a natural number. Hold on a second. for every real number c. I don't know why this sentence is needed, huh? We have also shown that for every real number c, there exists a natural number big N, such that for all, for all, actually, yes, this is also true. So this is needed. This is actually needed. So here, because earlier, this is what we shown. The set is unbounded. So by the claim, for every c in real, okay, there exists n in the set of integers. Well, if there exists n in the set of integers, then there exists n in the set of natural numbers, such that q to the n is greater than c. And next up we have, since q is greater than 1, for every little n greater than this little n, how should I put this? So for every, let me use a big N here, big N. Okay, this is, I figure I should probably rephrase things a little bit. Okay, I want to rephrase things as such. Since q is greater than 1, or 1 is less than q, then for this big N, for all n greater than big N, q to the little n is greater than c as well. Okay, so that's the second paragraph in the proof. So it says, so let c to be 1 over epsilon. Okay, so let c to be epsilon, we have, then there exists big N in the set of natural numbers, such that for all little n greater than big N, if q to the little n is greater than 1 over epsilon. Or you can write it as 1 over q to the little n, q to the little n is less than epsilon. Yeah. Perhaps we should use a different letter, huh? Exist big M. Why don't we say big M? Just to avoid confusion here. And little m greater than big M, such that q to the m is greater than 1 over epsilon, or q to the 1 over q to the m is less than epsilon. Okay, so that's what we are getting at. Okay. So here, it then says, thus the set of integers satisfying the inequality I'm a little bit confused here. I'm a little bit confused here, so what is going on? I think the proof is a little bit overly complicated. Here, let's see be this x positive. We haven't even used this positive x yet. Okay, I kind of dislike the original proof. So basically, I don't think this is needed. So, okay, I'll do this for the rest of the study. So basically, I'll try to first prove the lemma or the whatever result myself first, and then I'll try to follow the argument. Because sometimes the original exposition can be a little bit confusing because we haven't even used this big X, this X greater than 0. So now let X greater than 0. Okay, let X greater than 0. Okay, let X greater than 0 by above there exists a okay, guys, I'll try to put I'll put the screenshot here, okay, because I don't really know what is going on. Why do we even need this? Okay, so we have so far we have this part, we have this part, we have this part, okay, and it says it follows from what we have earlier that for any epsilon there exists big N, big M, such that 1 over q to the m is less than epsilon for all natural numbers m greater than big M. Okay, I mean, there's nothing wrong with this sentence. I just don't see how this is helpful for what follows. Indeed, it suffices to set c equals 1 over epsilon and n equals big M. Yeah, this sentence is also correct. And it says here, this is a crucial link. It says the set of integers m satisfying the inequality x less than q to the m for x greater than 0 is bounded below. Let's write that. It says m such that m in z such that x less than q to the m. This is bounded below. Why? Okay, so why don't we call that a second claim? Claim number 2. This set is bounded below. The set of integers such that x, okay, less than x is positive, it's a positive number. This is bounded below. So why don't we do another contradiction and say if this is unbounded below, so m can be as small as you like. If this is unbounded below, then what? So then q to the m can be arbitrarily small, right? That's the intuition. Q to the m, if m can be minus infinity, then the right-hand side can tend to 0, which is not allowed. Right, so say assume this is unbounded below. I want to give a formal argument. If this is unbounded below, then you can, how can we get a contradiction? Then x would be less than, say, unbounded below. Okay, can we let minus n, so say minus n be a so let any n be a natural number. X to the minus n is less, sorry, x is less than q to the minus n. Assume this is unbound below, then there. Okay. I think my brain just went blank. I don't know why this is. I fail to see why this is unbounded below. This is bounded below. I mean, I know this is intuitively true, right? Because q to the m will tend to 0. The x is here, right? So eventually q to the m will approach 0 as m tends to infinity. As m tends to infinity. So the set m of integers, the set m of integers such that x is less than q to the m cannot be as large as you like. Therefore, it is bounded below. What? Guys, because q to the k is not bounded above. Is not bounded above. So is okay, since q to the k is not bounded above, so you see that we show that for any epsilon we have an infinite sequence decreasing element of 1 over q to the n that are less than epsilon but greater than 0. Yes, that's the intuition, right? So these are the points q to the m. As m tends to infinity, this will eventually approach 0. But x is strictly greater than 0, so m cannot tend to infinity. That's basically it. But I wanted to give a formal argument here. Q to the k is unbounded above. Here we say for every epsilon greater than 0, there exists m such that 1 over q to the m is less than epsilon. But we want q to the m to be greater than x. Right? We want q to the m to be greater than x. Okay. I see. I mean, intuitively, this is all quote-unquote obvious, but how do you write it up? Here we say by the claim for every c greater than, for every c in R, right? For every c in R, there exists an big N in the set of natural numbers such that q to the n is greater than c. Guys, I apologize for the confusion. Since q is greater than 1, then for all n greater than big N, q to the n is greater than c. Is greater than c. So is this needed? Yeah, this is needed. This is needed. So the point is, let x be positive. Let x be positive. So eventually, x is less than x. Hold on a second. This is wrong. This is wrong. This is completely wrong. Q is greater than 1. What am I talking about? I must be drunk today. I must be drunk today. So let x be positive by above. Eventually, q to the m will be greater than x. Right. eventually q to the x will be greater than x. So by above there exists a x to the m. What does it say? Here it says, what does the set of integers m satisfy the inequality x is less than q to the m for x greater than 0 is bounded below. Is it bounded below or above, huh? This is x right here. X is a positive number. Q is greater than 1. Oh, right. If m tends to minus infinity, then that's, if m is negative, if m is, say, tends to minus infinity, then the right-hand side tends to 0. Yeah, that's the original motivation. That's correct. That's correct. I still don't see this. Guys, please send help. It's, okay. Okay, I'll delete this. Okay, so this is still unclear to me. The claim is that the second claim is that claim 2 is that the set of integers the set of integers m in big Z such that, okay, hang on, let me rewrite this. For every x greater than 0, for every x greater than 0, real x greater than 0, the set m in the set of integers such that x is less than q to the m is bounded below. How? Because if you have that, then you have the uniqueness. And so now, okay, Tep, I don't know if I can follow you. Okay, it's not your fault. I'm suffering from a brain fog right now. So you see, we showed that for any epsilon we have an infinite sequence of decreasing elements 1 over q to the n that are less than epsilon but greater than 0. I suppose, although I can't even make sense out of that now. And now simply inverse both sides. 1 over epsilon is less than the infinite sequence. It's important that the power of q is integer, so the picture should have points on both sides of x. Okay. I don't know. Like right now I'm a little bit confused. Perhaps more than a little bit. So this set of integers is bounded below. This is what we want to show. What do we mean by that? That is to say, there exists C in real such that for all m greater than C, greater or equal to C, okay, for all m greater or equal to C, x is less than q to the m. Right. This set is bounded below means there exists a lower bound. C, let's call C the lower bound. the lower bound C has this property. This is what we need, right? You need to show this is bounded below. Therefore, you need to show there exists a lower bound. You need there exists C, which is a lower bound. The lower bound satisfy what? I can't even translate that sentence right now. I am completely brain screwed. So what do you need? We need the set, there exists C, a lower bound for the set M in Z, X is less than Q to the M. Okay, this is what we need. What do a lower bound need to satisfy? This means for every M greater than C. What does the lower bound need to satisfy? Send help. Please send help. If there exists C, a lower bound for the set. So this means if M is greater than, if M is in the set, if M satisfies this property, meaning if X is less than Q to the M, then M must be greater than C. Yeah. Right. This set is bounded below because the intuition is quite simple. Right, this is 0, this is X. Q is greater than 1. So for M tends to minus infinity, Q to the M approach 0, and therefore M cannot be minus infinity. Therefore M cannot be minus infinity. Right? As M tends to infinity, Q to the M tends to 0. Q to the M tends to 0. Can we maybe just translate this? Q to the M tends to 0. Because Q is positive, right? Q is positive and Q is greater than 1. We have Q is greater than 1. What we have earlier, we said this set Q to the K is not bounded above. Can we say Q to the M tend to 0 or something similar to that? Chat. Yeah. If M belongs to C, you use Bernoulli identity, right? If you use Bernoulli identity, this is trivial. You see? I use Bernoulli identity here because I'm trying to follow Zorich's original proof, but I couldn't. So, and I try to do it in a way that does not depend on Bernoulli. I know if you use Bernoulli, then it's easy because it converts to a linear function. You want to talk about log without saying log, basically, in this problem. Yeah, so where we're stuck, which page are you on? A great question. Great question. So I'm on page 62. I'm on page 62. Okay, guys, let me clear my head a little bit. We need the lemma from section 2.2.4. It says the following. If a number Q is greater than 1, then for every positive number X, there exists a unique integer K, such that Q to the K minus 1 is less than or equal to X, and is less than q to the k. This is what we want to show. Okay, so we start with our first claim that q to the k, the set q to the k, k is an integer, is not bounded above. Okay, so this is a clean application of the least upper bound principle. So we're good with that. And now we need to show a second claim. That is to say, which says, for any x greater than 0, the set of integers m, such that x is less than q to the m is bounded below. And here's the intuition for that claim. X is positive, q is greater than 1, q to the m will tend to 0 as m tends to minus infinity. Right? And therefore become less than x. Eventually it will go below x. So q cannot tend to minus infinity, and therefore m has a minimum value. That's the intuition. But how can we prove it? Not with picture. Because what we have earlier should be useful. Q to the k is not bounded above. Since q to the k is not bounded above, this set is not bounded above. Okay, by our claim, let me just remove that. This is claim 1, all right? By claim 1, this is not bounded above. What can we say about x here? Well, by claim 1, x is not an upper bound. Of q to the k. K is an integer. It has no upper bound. So therefore, there exists k in the set of integers such that q to the k is greater than x. Which is the same as x is less than q to the k. Can we replace epsilon by 1 over x in the previous statement? Yeah, it has something. I think that's where we should be heading. Yeah, I totally agree. We should use claim 1, right? By claim 1, there exists k such that x is less than k. X is less than q to the k. I totally agree. Okay, let me just follow my own advice and write let x greater than 0. X is not an upper bound, therefore there exists k is an integer such that x is less than q to the k. And since q is greater than 1, for all n greater than k, for all m greater or equal to k, x is less than q to the k is less than q to the m. less than or equal to q to the m. Okay. So what we managed to show? We managed to show that for x greater than 0, there exists a k such that for all m greater or equal to k, x is less than q to the m. What can we say about this set? What can we say about this set? This says it's bounded below. Is this saying that the set is bounded below? I cannot tell. Guys, I'm completely and mentally exhausted by this stage. Like, what the hell is going on? This m is an integer, m greater or equal to k. For all m greater or equal to k, x is less than q to the m. Commentator says there exists an m such that q to the m is greater than x. As q to the m as q to the m increases as m increases. So for any integer m greater or equal to m cannot be the set of integers such that. So m is an upper bound for this set. We want to show the lower bound. We want to show the set of integers m such that x is less than q to the m is bounded below. What does this freaking sentence mean? It has a lower bound. I want to show this has a lower bound. This is embarrassing as hell, I know, guys. But I'm not gonna move on and say, okay, I'm done with this problem. Screw it. Okay, but let's try to. I'll try to calm down and finish this through. I have half an hour left, so I'll try to finish this claim in that time period. Okay. The set M. Want to show this set M is bounded below. Actually, you know what? I'm getting lost. Why are we even doing this? How is this relevant to the lemma? In the book, it says, okay, let's just take this for granted. Okay, if we take this sentence, say, if this assume this is okay, because this is quite intuitive, even though I'm completely just unable to get a justification. So it has a minimal element. That's true. This is a property of the set of integers. This is a property of the set of integers because there is something called the well-ordering property of integer. It says if a set of integer is bounded below, then it must have a minimum element. This is equivalent to induction, to the principle of mathematical induction. It can be, in fact, it can be seen as the defining property of the set of natural numbers, actually. But anyway, we should have no problem with this. Okay, if we have the the question sentence. I know this is correct, but I can't prove it. Okay, I'm stuck. But if we can take that sentence as granted, oh, okay, I'll read chat in a bit. Okay, if we take the sentence as granted, then there exists a minimum element k, which obviously will be the one we're seeking. Which obviously will be an element okay, so k satisfy x is, yeah, this is a minimum element, right? This is minimum because by k is such an element, therefore x is less than q to the k. And by minimality of k, if you let k be go down by 1 unit, right, then it will fail the inequality. Okay, so this shows existence. And now for uniqueness, the uniqueness of such an integer k follows from the fact that if n and n are integers, for example, m is less than n, what? M is less than n, then m is, this is trivial, m is less than or equal to m minus 1. Hence, if q is greater than 1, then q to the m is less than q to the m minus 1. Okay, how is that relevant to uniqueness then? It can be seen from this remark that the inequality I don't know why do we need this extra part, because if k is a minimal element, obviously this is unique. Why can't we say because k is a minimal element, it must be unique? Right? Any other integer is either greater than k or less than k. Less than k doesn't work because we have this. If it's less than k, then x is already greater or equal to k minus 1. I don't even know why do we need this part. This is a very puzzling proof. Okay, I'll come back to chat. Chat says C, oh, I erased it probably. C is 1 over x, hence there exists. Yeah, hence there exists. Thank you very much, Mason. You actually Googled, I guess you Googled the belongs to symbol for writing such. Yeah, thank you guys so much for trying to help me. It's just my brain is completely fucked. Sorry for the bad word. That I can't follow what is going on, either in chat or in the book. Okay. When that happens, it's usually a good idea to do something else. Take a walk, pet your cat, go grab a cup of water, and then come back. I should probably do that. But, I mean, I have 20 minutes left. I want to see if I can finish off this problem. Because, guys, this is another thing I'm struggling with, right? So why do we need this part? Why can't we just say k is unique simply because of it's the minimal element? Because this is a minimal element k, right? So obviously, if an integer is less than k, the property fails. This property would fail. If k is if something, let's say L is less than K, then L would not satisfy this result. No, writing a software didn't Google the sign. Okay, I always Google the sign, like less than. When did we prove the uniqueness of minimal element? The minimal element is always unique, no? If I recall correctly. I don't know. Like perhaps it's in the earlier part of the book. The minimal element, because if I recall correctly in my own background, I know that the set of integers has this well-ordering property. The set Z has well-ordering property. If a set is bounded below, then it must have a minimum element. Why? Because if it doesn't have a minimum element, you can keep subtracting one at a time. If it does not have an element, then if you keep subtracting 1 minus 1 minus 1 minus 1, then you get a contradiction, right? But Zorich hasn't yet. I don't think you need to prove it, right? That's the fundamental property of integers. The property of integers is assumed in the book, I believe. Maybe I don't know what I'm talking about because I'm not super familiar with this text. Okay, okay, guys. So yeah, for those who join the stream later, because in this fifth example of a limit, okay, we need the lemma. The limit of 1 over q to the n is 0. We need the lemma. So now we're trying to prove the lemma without using the Bernoulli's inequality. Oh, hi Hiroshi, thank you very much for joining the stream, even though I'm not currently in my best, let's just put it that way. But I wish to do something like this. So I wish to, okay, guys, I will just try to prove this as an exercise. I'll try to not to follow the main text. Okay, I'll just do it myself. Because I was trying to follow the main text, and if, let's say, without any interference whatsoever, how do we prove this? How do you prove this yourself without looking at the book? Here you have, let's start with our template. Our usual strategy for proving things, proof. Assume the if part. Assume q is greater than 1. Okay, assume q is greater than 1. So because for every, right, because here we have for every, let x greater than 0. Okay. There exists a unique integer k such that this is true. So we claim the set of integers the set n, let's say the set n in Z, okay, and in Z such that x is less than q to the k is bounded below. This is what we claim, right? The claim immediately implies the result. Indeed, since this is a subset of n, this is bound is actually is non-empty and bounded below. Okay, I need the non-emptiness as well. Is non-empty and bounded below. Indeed, because this is a subset of Z, this is by the well-ordering principle. So the well-ordering principle says the following: if a set S is a subset of Z, it is bounded below and it is non-empty, then it must have a lower bound. And then it must have, sorry, not a lower bound, but it must have a minimum element. Well-ordering principle, which says if S is a subset of Z and S is non-empty, then S has a minimum element. Minimal. And it has to be, the minimal element has to be unique. Because Z has a total ordering, right? It's not a partial ordering. Right? It is a partial ordering, but most importantly, it is total ordering, which is unique. By the well-ordering principle, there exists here. This should be n, not k. There exists k in a set of integer such that k equals the minimum of the set, and in big Z, x is less than q to the n. Okay, since it's a minimum, it belongs to the set. So x is less than q to the k, and since it's a minimum, x is greater or equal to q to the k minus 1, and we're done. So it all hinges on this claim. This set is non-empty and bounded below. So let's show non-emptiness. Proof of claim. So let's do it that way, okay? Proof of claim. So how do we show this is non-empty? That is to say, there exists an integer such that x is less than q to the n. Can we do that? Yeah, for existence, well-ordering, and it's also unique. When you're reading a book, do you always try to prove the theorem before looking at the proof? It depends, right? It actually depends. If it is a subject that I have some experience with, I try to come up with my own proof before looking at the proof in the text. If I get stuck, I'll take a look at it. So that's generally the strategy. If I'm learning something for the first time, I usually just follow the textbook. Hopefully in the process, I'll save some time. So proof of the claim, we want to show this is non-empty. That is to say, there exists an integer. So non-empty part follows from the fact that q to the n is unbounded above. Okay. So yeah, the non-empty part, the n, there exists at least one n, right? There exists at least one n. Non-empty. Okay. So non-empty part. Assume for a contradiction, this will be similar to what we did earlier. Assume for a contradiction that there does not exist n in the set of integers such that x is less than q to the n. This means for all n in big Z, that's the negation of quantified statement, which we will come back to in our introduction to proof series. X is greater or equal to q to the n, i.e. the set q to the n such that n is an integer is bounded below, is bounded above. How did you prove that it has min and now the inf? Because this is a set of integers. Okay, the set of integers, the well-ordering principle is for integers only. Okay, so if the idea is okay, S is not empty but is bounded below. Is bounded below. Yes. This is there's a crucial assumption missing. S is bounded below. Okay. If it does not have a minimum element, it will contradict the bounded below part. If S is a subset of Z, S is not empty and S bounded below, then S must have minimum element. This is a well-known fact for integers. Let's see why. Okay, so if S has no minimum element, right, if S has no minimum element, then we are using the well-ordering. Yeah, this is well-ordering principle, not the completeness axiom. Okay, this is purely a property of integers. Yeah, well-ordering principle can be shown to be equivalent to mathematical induction. Okay, so I think we can just use this. Okay, and then move on with proving the claim. Okay, here I'm saying the claim immediately implies the result. And now I'm trying to prove the claim. Here, assume for contradiction that there exists no n. Now, assume the set is empty. That means there exists no n such that x is less than q to the n. That means for all n in Z, x is greater or equal to q to the n. That means q to the n is integer is bounded above. Bounded above. So now you can use the completeness axiom because q to the n is a subset of real. So which is clearly non-empty. Q to the n in big Z is clearly non-empty. And now bounded above. By the least upper bound principle, LUBP, it has a least upper bound. It has a sup. Okay, it has a sup. Say S. Say S. Okay, so therefore S over Q is not an upper bound. Of q to the n in integer. Since q is greater than 1, so therefore there exists m in Z such that S over Q is less than S to the M. It's not an upper bound, which means for this Q, there exists M in Z such that S is less than S is not S, but Q to the M. S is less than Q to the M plus 1. A contradiction. Since S is supposed to be an upper bound, it's supposed to be a sup, so it's a contradiction. Okay, and so therefore to conclude, there must exist n in Z such that X is less than Q to the N. The non-empty part is now shown, and now we need to show this is also bounded below. The set is bounded below. The set is bounded below. So need to show. What do we need to show? Need to show there it is bounded below. Again, should we use a contradiction? Yeah, let's use a contradiction. Assume the set is not bounded below. Assume this set is unbounded below. Okay, and then what happens? So the integers n can be as small as we like, basically. Assume this is true, then then what? Then is this unbound below? Then for all n in Z such that for all n in Z, if X is less than Q to the M, then X is less than Q to the M minus 1, no? Because this is unbounded below. Since Q to the N is increasing, in N. No, this is not what we want. Guys, I run out of time, okay, so I have to close it today. I know this is very disappointing. Sorry about that. But I don't want to gloss over this lemma because I have to leave. Okay, I'm sorry. I'm very sorry today. Today is not a very good day. It's not a productive day. Perhaps I shouldn't start a stream today because I have to leave. Okay, guys, I profusely apologize for this. Well, how should I put this? But basically, I can't do. Yeah, I figured it out. Okay, great. Guys, if you're if you if you're interested, you can. If you're bothered, okay, you can send your attempt or your proof to my Discord server. I'll take a look at it later. Okay. Okay, I have to leave. Sorry about that. Bye.